Hi there, my name is Digvijay. Welcome to this video on energy conversion technologies. In this lecture, we will look at the existing energy conversion technologies which include power to gas, fuel cells, power to heat, and combined heat and power. All these technologies are explored to present a broad overview of their role in coupling the energy systems. Let us start with power to gas systems. Power to gas technology, or P2G technology, has recently emerged as a go-to option in the energy transition equation. At its core, P2G works by converting electrical power into gaseous fuels. Most P2G systems use electrolysis of water to produce hydrogen. However, other systems which produce gaseous fuels such as methane or syngas using electricity are also being developed. Electrolysis is mainly of three types: alkaline, proton exchange membrane or PEM, and solid oxide cell or SOC electrolysis. Alkaline electrolysis has been around the longest, with capacities up to 100 megawatts being used in industrial setups. The technological readiness levels or TRL for alkaline electrolysis is 9, implying that it is a fully mature technology in deployment. The PEM electrolysis has recently gained a lot of traction for its high efficiency and stability. Currently, the largest available PEM electrolyzers are less than 10 megawatts in size, but are quickly approaching the scale of alkaline electrolyzers. The TRL for PEM electrolyzers is between 8 and 9. Lastly, we have the solid oxide cells, which are still in prototype and development phase, hence the TRL of 5. The SOC electrolyzers have higher energy efficiency and power density compared to PEM and alkaline electrolyzers, allowing for smaller and compact system design. Apart from producing gaseous fuels and chemicals, P2G has other operational advantages as well. All three mentioned technologies have extremely fast power response. Thus, it can help the power system respond to changes in real-time power balance, thereby helping in maintaining frequency of the power system and ensuring its stability. While power to gas converts electricity into gaseous fuels, fuel cells do exactly the opposite by converting gaseous fuels such as hydrogen and oxygen into electricity. Fuel cells were developed in 1830s but found their use in critical power supply in mid-1960s when the National Aeronautics and Space Administration, or NASA, started using them to power satellites and space capsules. Fuel cells work by converting chemical energy into electrical energy. As seen here, at the anode, the hydrogen is oxidized, which generates positively charged hydrogen ions and electrons. These travel to the cathode via the electrolyte medium, when at the same time electrons move from cathode to anode via the external circuit, producing direct current. In large fuel cells, these smaller cells are stacked together so that the amount of current and consequently the power produced is significant. The largest fuel cell at the moment of recording this lecture is installed in South Korea with a capacity of 59 megawatts. The International Energy Agency, in its 2018 report, explained that although heat accounted for half of global energy consumption, only 10% was produced using modern renewable energy. The power to heat technology could be used to convert electricity into renewable heat. This heat can be for residential, commercial, or industrial use in the form of either hot water or steam. Power to heat is achieved either through electric boilers or electric heat pumps, both of which are highly efficient technologies. The boilers are simple in operation and can be based on either electric resistive heating or a combination of both gas and electricity. Both boiler systems are more efficient than gas boilers since using electric resistive heating is a 100% efficient process. Electric heat pumps can be air, ground, or water source heat pumps. Here, the term source refers to the medium used for heat exchange. Heat pump performance is measured with a variable called coefficient of performance, or COP. COP is the ratio of useful heat, or cold, provided to the energy input. Consider this figure. Heat pump is a device that transfers heat energy from a heat source to a heat sink, but in this case, the transfer occurs in the opposite direction of normal heat transfer. The heat pump absorbs heat from a cold space, as shown QC, and uses electrical power, W pump, to transfer this heat to a warmer space, as shown here, QH. The COP of a heat pump is therefore the ratio of QH to W, where QH is the sum of QC and W. Therefore, the COP for heating is always greater than 1. In actual applications, the COP ranges from 2 to 6. Power-to-heat systems can also be used to support electrical power systems and help integrate greater share of renewable energy into the grid. However, unlike power-to-gas systems, which are highly effective at providing frequency regulation, power-to-heat systems are excellent at shifting their power consumption in time, making them excellent candidates for peak shaving and valley filling purposes. Till now, we have looked at technologies which use fuel and produce either gas or electricity or heat. Let us look at a technology that converts one fuel into two energy forms. This is known as cogeneration, or combined heat and power, or CHP for short. It converts fuel, typically natural gas or biofuel, to heat and electricity. CHPs have a primary objective, which is either to produce electricity or heat. If the primary objective is to produce electricity, then waste heat from electricity generation process is recycled to serve a thermal demand. Alternatively, if the primary objective of the CHP is to serve a heat demand, whether it is hot water for district heating or high pressure steam for industrial process, then waste heat is used to generate electricity. In either case, since the CHP uses its waste heat, it is a very efficient process. And this is one of the primary reasons that CHP technology is prevalent around the world. CHP capacities can range from 30 kilowatts to 300 megawatts, although there are some even larger plants in operation. One of the largest CHP installations is in Sweden, where the CHP plant produces 130 megawatts of electricity and 280 megawatts of thermal power. Gas turbine CHPs can quickly start up and produce power, and hence are used extensively as peak power plant generators. This means that at times when the power system needs quick production of electricity to supply a peak demand, these generators can be called upon at a moment's notice to contribute. Their ability to quickly ramp up the electricity output can be used by system operators to maintain the supply and demand balance and keep the power system stable. To recap, we looked at various energy conversion technologies such as power to gas, fuel cells, power to heat, and combined heat and power. We looked at individual capacities of these technologies, their potential, and how they could be beneficial to an integrated energy system of the future. We also covered the application of these technologies in supporting the electrical power grid, specifically frequency support and peak load shifting. Thank you for watching and see you next time.